7.1 is exploring the characteristics of exponential functions. So what we're trying to do is take a look at what an exponential function and identify some of the characteristics that we can use to help us graph it or identify what a graph would look like. So an exponential function is a function of the form y is equal to a b to the power of x, where a is not equal to 0 and b is greater than 0 and b cannot equal 1. So we're going to take a look at a couple of graphs and just compare what happens when we change a value. So for the first one, we have the function of x is equal to 10x. So all we're going to do is substitute these values in to the exponent and see what happens to our answer. So if we do 10 to the power of negative 3, that equals 0.001. I can change my color there. Negative 2, 10 to the power of negative 2 is 0.01. Negative 1 will be 0.1. 10 to the power of 0 is 1. 10 to the power of 1 is 10. To the power of 2 is 100. And to the power of 3 is 1,000. So now when we go to plot these, at negative 3, our answer was 0.0001. So it's pretty close. Oops, I see my alignment is off. I'm just going to pause and fix that real quick. Okay, so now to plot these. Negative 3 and 0.001 is almost touching that line. Negative 2 and 0.01, so it's, again, almost touching that 0, but a little bit above it. Negative 1 to the power of, 10 to the power of negative 1 was 0.1, so again, it's barely registering as off of the 0 on the x-axis. Then we get to 0, and our value is at 1. So we're going up by 100s on here, so you can see it's not going to be making a large shift off of that x-axis. Then when we were at 1, it was at 10. When we were at 2, it was at 100. 3, it went all the way up to 1,000. So if you take a look at our graph, it's doing this. It's almost touching the 0, but not quite. And then as we get into the positive exponents, it grows incredibly. So remember, when we're reading these equations, we always read from right to left. So this equation would start in quadrant 2 and would end eventually in quadrant 1. So it gets closer and closer and closer to 0, but it doesn't cross that 0. So what happens when we change our value so that we're finding 2 times 5 to the power of x? So this time we have an a and a b value, whereas last time we just had that b value. Our a would have equaled 1. I should have wrote that in here. So for this is the same as saying f of x is equal to 1 to the power of 10, or 1 times the power of x. So for this one, when we do negative 3, you have to remember when you're doing this, it's 2 times 5 to the power of negative 3. So that negative 3 exponent applies only to the 5. So that's the same as saying 2 to the power, or 2 times 1 over 5 cubed. And 5 cubed is 125. So 2 divided by 125 is 0.016. So the same thing here, then we'd be, for negative 2, we'd have 2 to the power of negative, or 5 to the negative 2. So that'd be like 2 over 100, which reduces to 0.08. Put that to the power of negative 1. That's 2/5, which is 0.4. To the power of 0 would be 2 times 1, so it's 2. Power of 1 would be 5 times 2, so it's 10. 5 squared is 25 times 2, so that's 50. And power of 3 is 125 times 2, so that's 250. So when we graph these, at -3 it was 0.016, so again just barely off the 0. At -2 it was 0.08, so getting a little bit higher but not very far. -1 was at 0.4. 0 got us all the way up to 2. 1 got us up to 10. 2 was at 50. And then 3 was at 250. So again, you can see the higher the power, the positive power, the quicker this graph grows, or the higher it goes. So again, it's starting in quadrant 2 and ending in quadrant 1. So what if you have a fraction, 1/2 to the power of x? So for an exponent of -3, this is 1/2 to the power of -3. So a negative exponent means you flip it. So this becomes 2 over 1 cubed, or just 2 cubed. So that becomes 8. To the power of -2, that's going to be 1/2 squared, so that's 4. To the power of -1 will be 2 to the power of 1, so that's just a 2. 0 will be 1. So what happens when I put in a 1? It's just going to stay 1/2. When I put a 2, it's 1/4, or 0.25. To the power of 3 would be 1/8, which is 0.125. So when I go to plot these at -3, it was up at 8. Whoops, 3 and 8. 2 and -2 and 4. -1 and 2. 0 and 1. 1 and a half. It was 2 and a quarter. And 3 and 1/8. So you can see it starts quite high, and then it gets smaller and smaller and smaller. So again, this graph would have, and behavior would start in quadrant 2 and end in quadrant 1. The only difference is what your values are. So what if we had an a value? So in this one, our a would be, because this is the same as saying 1 times 1/2 to the power of x. So our a would be a 1. In this case, we have an a value of 8. So 8 to the 1/4 x. So again, when we put in our exponents, we'd have 8 to the times 1/4 to the power of -3, which is 8 times 4 cubed, which equals 512. To the power of -2, then, we would have 4 squared, which is 16, times 8 is 128. To the power of -1 would be 8 times 4, so that's 32. To the power of 0 would be 8 times 1, so that's 8. 8 times 1/4 to the power of 1 is just 8 divided by 4, so that's a 2. To the 1/2 would be 8 over 16, so that's a half. And to the power of 3 would be 8 over 64, which is 0.125. So if we go to plot these, at -3, we were at 512. So 512, 525, so it's about approximately right there. -2 and 128, be just a little over half. -1 and 32. 0 and 8. It was 1 and 2. 2.5. 3 and 0.125. So you can see it's getting closer and closer and closer to 0. So our graph does this. So again, it starts in quadrant 2 and ends in quadrant 1. So in summary, for exponential functions for the form fx is equal to a to the bx, where a isn't equal to 0, b is greater than 0 but not equal to 1. So what we found when we had fx is equal to 10 to the power of x, the number of x-intercepts we had was 0. It never crossed that x-axis. Our y-intercept, so y-intercept is found when we have 0 for the x value and find the y. So for this one, it was 1. Number of x-intercepts for 2 times 5 to the power of x, so again, it never crossed that x-intercept. The y-intercept was when you substitute the 0 in there. So it was 2 to the power, if x is a 0, it would be 5 to the power of 1, which is, excuse me, 5 to the power of 0, which is 1. So 2 times 1 is 2. When we had it to the 1/2, the graph never crossed that x-axis. It got close to 0, but it never crossed it. When we find the y-intercept, 1/2 to the power of 0 was 1. And then for the last one, when we did 8 to the power of 1/4 x, again, it never crossed that x-axis. We had 1/4 to the power of 0 would be 1, so 8 times 1 is 8. So what we notice is the y-intercept is equal to, the a value. Our end behavior. For every single one of these graphs, it started in quadrant 2 and would end eventually if we had an end in quadrant 3. Our domain, we could use any x value we wanted. However, our range, we never crossed that x-axis, so it never went below 0 on the y. So it's y is an element, or y is greater than or equal to 0, y is an element. So it shouldn't be equal to, it should just be greater than, because we never touched the x-axis. We never actually got a 0. What the other thing you might notice is when whenever we had our function y is equal to a times b to the power of x, and our b value was greater than 1, so like this one and this one, our graph went in a specific direction. So our graph started low in quadrant 2 and went up in quadrant 3, or sorry, in quadrant 1. When we had a fraction, so when our b value was in between 0 and 1, our graph went in this direction. So it started high in quadrant 2 and went closer and closer and closer to 0 in quadrant 3. Sorry, quadrant 1. I keep wanting to say quadrant 3. So you have your questions to work on for this section.